Can you spot the idea that unlocks each one? A tank draining, modeled with a differential equation. Vector lines cutting at an angle. Complex numbers traced on the Argand plane. Partial fractions feeding a series. A curve with a minimum and the area beneath it. An equation whose root you chase step by step. Trig identities that become graphs. Implicit differentiation. Integration by parts. Factors and remainders. Every step is on screen. Every line is explained. Question 1. Factor and Remainder Theorem. Pure Mathematics 3, October-November 2024. The polynomial p of x equals 4x cubed plus ax squared plus 5x plus b, where a and b are constants. 2x plus 1 is a factor of p of x. When p of x is divided by x minus 4, the remainder equals 3 times the remainder when divided by x minus 2. Find the values of a and b. Now let's work through the solution step by step. First, the factor theorem. If 2x plus 1 is a factor, then p of negative 1/2 must equal 0. Substitute x equals negative 1/2 into p of x. Collecting terms gives negative 1/2 plus a over 4 minus 5/2 plus b equals 0. So a plus 4b equals 12. Next, the remainder theorem. Dividing by x minus k leaves remainder p of k. So p of 4 and p of 2 give the two remainders in the question. First evaluate p of 4. Then evaluate p of 2. Use p of 4 equals 3 times p of 2. Simplify the algebra. This gives 2a minus b equals negative 75. Now solve the pair of simultaneous equations. Write both equations. From the first, a equals 12 minus 4b. Substitute into the second equation. So b equals 11 and a equals negative 32. The values are a equals negative 32, and b equals 11. And that completes question 1. Question 2. Integration by parts. Find the exact value of the integral from 1 to 3 of x squared natural log of 3x, dx. Give your answer in the form a log b plus c, where a and c are rational and b is an integer. Now let's work through the solution step by step. This is a logarithm times a polynomial, so we integrate by parts. Let u equal natural log of 3x, so du by dx is 1 over x. Let dv be x squared dx, so v is x cubed over 3. Substituting gives x cubed over 3 log 3x, minus x cubed over 9. Now apply the limits from 1 to 3. Remember that log 9 equals 2 log 3. Evaluate at 3 and subtract the value at 1. This gives 9 log 9 minus 3, minus 1/3 log 3 minus 1/9. Collect the log 3 terms. So the exact value is 53 over 3 log 3 minus 26 over 9. The exact answer is 53 over 3 log 3 minus 26 over 9. That completes question 2. Question 3. Implicit differentiation. The equation of a curve is log of x plus y equals 3x squared y. Find the gradient of the curve at the point 1, 0. Now let's work through the solution step by step. Differentiate both sides with respect to x, using the chain rule and product rule. For log of x plus y, the derivative is 1 plus dy by dx, over x plus y. For 3x squared y, the product rule gives 6xy plus 3x squared dy by dx. Equating both sides gives 1 plus dy by dx over x plus y, equals 6xy plus 3x squared dy by dx. Now substitute the point x equals 1 and y equals 0. The left side becomes 1 plus dy by dx, over 1. This simplifies to 1 plus dy by dx equals 3 dy by dx. So 1 equals 2 dy by dx. The gradient is dy by dx equals 1/2. That completes question 3. Question 4. Trigonometric Identities. Part A. show that sec to the fourth theta minus tan to the fourth theta is identically 1 plus 2 tan squared theta. Part A. Prove the identity. Start with the left-hand side. Write each term as a square. This is a difference of two squares. A squared minus b squared equals a minus b times a plus b. From the Pythagorean identity, the first bracket equals 1. So we replace the first bracket by 1. 1 times the second bracket, the expression simplifies. Now use the identity again, rearranged, to replace sec squared. Substitute into our expression and keep the brackets. Remove brackets, plus between the terms. Combine like terms, 2 lots of tan squared theta. Part B. Hence solve sec to the fourth 2 alpha minus tan to the fourth 2 alpha equals 2 tan squared 2 alpha sec squared 2 alpha, 40 degrees less than alpha less than 180 degrees. Now let's work through the solution step by step. Part B. Solve for alpha between 0 and 180 degrees. From Part A, sec to the fourth theta minus tan to the fourth theta equals 1 plus 2 tan squared theta. In Part B the angle is 2 alpha everywhere. Let theta equal 2 alpha. This is the Part B equation, 2 alpha appears in every term. Replace every 2 alpha with theta. Now the equation is written entirely in theta. The domain 0 less than alpha less than 180 becomes 0 less than theta less than 360. Use Part A on the left-hand side. Let t equal tan squared theta, so sec squared theta equals 1 plus t. Solving gives tan squared theta equals 1 over root 2. Take square roots on both sides, remember the plus or minus sign. So tan theta equals plus or minus the square root of 1 over root 2. First the plus sign. Tan theta equals plus root 1 over root 2. To find theta, apply inverse tan to both sides. Inverse tan undoes tan. So theta equals inverse tan of root 1 over root 2. On your calculator, in degrees mode, that gives 40.06 degrees. That is the first answer in quadrant 1. But tan is not 1 to 1. The same height on the graph comes back every 180 degrees. Use the identity, tan of theta plus 180 degrees equals tan theta. Add 180 to the first angle, 40.06 plus 180 equals 220.06 degrees. So for the positive root, theta equals 40.06 and 220.06 degrees. Now the minus sign. Tan theta equals minus root 1 over root 2. Inverse tan gives minus 40.06. The reference angle is still 40.06 degrees. Between 0 and 360, a negative tan value sits in quadrant 2. Theta equals 180 minus 40.06, which is 139.94 degrees. Use the same rule again. 139.94 plus 180 equals 319.94 degrees. For the negative root, theta equals 139.94 and 319.94 degrees. Finally theta equals 2 alpha, so divide each theta by 2. Alpha equals 20, 110, 70, and 160 degrees. So alpha equals 20 degrees, 70 degrees, 110 degrees, and 160 degrees. That completes question 4. Question 5. Locating a root. Part A. By sketching a suitable pair of graphs, show that 2 plus e to the power minus 0.2x equals natural log of 1 plus x has only one root. Now let's work through the solution step by step. Part B. Show by calculation that the root lies between 7 and 9. Now let's work through the solution step by step. On the right is the iteration plan. Follow each box in order. Build a 3-column table, n, x sub n, and x sub n plus 1. Row 0. n equals 0 and x0 equals 8.0000. Substitute into the formula to get x1 equals 8.0421. Copy that value into the next row as x1. Substitute again, x2 equals 8.0268. Repeat the same substitute, compute, and copy cycle for rows 3 to 5. The iterates agree to 2 decimal places 8.03. So the root is x equals 8.03. Question 6. Curve minimum and area. The curve y equals sin 2x times 1 plus sin 2x, 4x from 0 to 3 pi over 4. Part A. Given the x-coordinate of m lies between pi over 2 and 3 pi over 4, find the exact coordinates of m, the minimum point. Now let's work through the solution step by step. Sketch the curve on the interval from 0 to 3 pi over 4. Expand the product, y equals sin 2x plus sin squared 2x. Differentiate to get 2 cosine 2x plus 4 sine 2x cosine 2x. Factor, 2 cosine 2x times 1 plus 2 sine 2x equals 0. In pi over 2 to 3 pi over 4, sin 2x equals minus 1/2. So 2x equals 7 pi over 6, and x equals 7 pi over 12. Substituting gives y equals minus 1/4. So m is 7 pi over 12, minus 1/4. The curve y equals sin 2x times 1 plus sin 2x, 4x from 0 to 3 pi over 4. Part B. Find the exact area of region R above the x-axis. Now let's work through the solution step by step. Region R lies between 0 and pi over 2, where the curve is above the axis. The area is the integral from 0 to pi over 2 of sin 2x plus sin squared 2x. Use sine squared 2x equals 1/2 minus 1/2 cosine 4x. Integrate to get minus cosine 2x over 2, plus x over 2, minus sine 4x over 8. Evaluate between 0 and pi over 2. So the exact area is 1 plus pi over 4. That completes question 6. Question 7. Partial fractions and series. Let f of x equal 5x squared plus 8x plus 5, over 1 plus 2x times 2 plus x squared. Part A. Express f of x in partial fractions. Now let's work through the solution step by step. Express in partial fractions. The denominator has a linear factor and a quadratic factor, so we use this template. Multiply both sides by the full denominator to clear fractions. Pick x equals minus 1/2 because 1 plus 2x is then 0. That removes the bx plus c term, so a equals 1. Compare x squared terms on both sides, 5 equals a plus 2b, so b equals 2. Compare constant terms, 5 equals 2a plus c, so c equals 3. So f of x equals 1 over 1 plus 2x, plus 2x plus 3 over 2 plus x squared. Let f of x equal 5x squared plus 8x plus 5, over 1 plus 2x times 2 plus x squared. Part B. Hence find the coefficient of x cubed in the expansion of f of x. Now let's work through the solution step by step. Find the coefficient of x cubed. Before we expand anything, learn the binomial formula. 1 plus u to the power n equals 1, plus nu, plus nn minus 1 over 2u squared, and so on. The size of u must be less than 1. When n equals minus 1 you get alternating signs, 1 minus u plus u squared minus u cubed, continuing. In the first fraction use u equals 2x. In the second fraction use u equals x squared over 2. Now apply the formula. We expand each partial fraction, one at a time. Expansion 1. Only the first partial fraction, 1 over 1 plus 2x. From part A, f of x equals 1 over 1 plus 2x, plus 2x plus 3 over 2 plus x squared. Ignore the second term for now. Rewrite the first fraction as 1 plus 2x to the power minus 1. Use the formula with u equals 2x. Each power of u becomes a power of 2x. So we get 1 minus 2x plus 4x squared minus 8x cubed. Expansion 2. Now the second partial fraction, 2x plus 3 over 2 plus x squared. Take 2x plus 3 over 2 plus x squared. Factor out 1/2, 2x plus 3 over 2, times 1 over 1 plus x squared over 2. Inside, use u equals x squared over 2. We only need up to x squared, that is enough for an x cubed term. Multiply out to get 3/2 plus x minus 3/4 x squared minus half x cubed. Finally, add the x cubed terms from both expansions. From expansion 1 the x cubed term is minus 8x cubed. From expansion 2 the x cubed term is minus 1/2 x cubed. Add them, minus 8 minus a half equals minus 17 over 2. So the coefficient of x cubed is minus 17 over 2. That completes question 7. Question 8. Complex numbers and Loci. Given z equals 1 plus yi, with y real. Part A, express 1 over z as a plus bi. Now let's work through the solution step by step. Write 1 over z as a plus bi. Start with 1 over z equals 1 over 1 plus yi. Multiply top and bottom by 1 minus yi, the conjugate. The denominator becomes 1 plus y squared. The numerator is 1 minus yi. So A equals 1 over 1 plus y squared, and B equals minus y over 1 plus y squared. So A equals 1 over 1 plus y squared, and B equals minus y over 1 plus y squared. Given z equals 1 plus yi, with y real. Part B, show that a minus a half squared plus b squared equals a quarter. Now let's work through the solution step by step. Show the circle identity. First write a minus a half using the a from part A. Now substitute a and b into a minus a half squared plus b squared. Expand the numerator, 1 minus y squared squared plus 4y squared. That simplifies to 1 plus y squared squared over 4 times 1 plus y squared squared, which equals 1/4. So a minus a half squared plus b squared equals 1/4, as required. Given z equals 1 plus yi, with y real. Part C, sketch the Loci real part of z equals 1, and mod z minus a half equals a half. Now let's work through the solution step by step. Sketch the two Loci. Draw the Argand diagram. Real part of z equals 1 is a vertical line through 1 on the real axis. Mod z minus a half equals a half is a circle, center 1/2, 0, radius 1/2. The line touches the circle at the point 1, 0. Given z equals 1 plus yi, with y real. Part D. If the real part of z equals 1, describe the locus of 1 over z. Now let's work through the solution step by step. Describe the locus of 1 over z. From part B, whenever z has real part 1, 1 over z satisfies a minus a half squared plus b squared equals a quarter. So the locus of 1 over z is a circle with center 1/2, 0, and radius 1/2. The origin is excluded because z is never 0 on the line real part equals 1. So the locus of 1 over z is a circle, center 1/2, 0, radius 1/2, with the origin excluded. That completes question 8. Question 9. Vectors, lines, and angles. OA equals 8i minus 5j plus 6k. Line L passes through A, parallel to 2i plus j plus 4k. Part A, state a vector equation for line L. Now let's work through the solution step by step. Write the vector equation of line L. A line is every position vector r that equals a fixed point A, plus lambda times a direction vector d. Point A has position vector 8, minus 5, 6. The line is parallel to direction 2, 1, 4. So the vector equation is r equals a plus lambda d, with these column vectors. So r equals the vector 8, minus 5, 6, plus lambda times 2, 1, 4. OA equals 8i minus 5j plus 6k. Line L passes through A, parallel to 2i plus j plus 4k. Part B. B has position vector minus ti plus 4tj plus 3tk, and B lies on L. Find t. Now let's work through the solution step by step. Find t so that B lies on L. If B lies on L, then minus t, 4t, 3t equals 8 plus 2 lambda, minus 5 plus lambda, 6 plus 4 lambda, using the same lambda in all three components. From the j component, 4t equals minus 5 plus lambda. From the I component, minus t equals 8 plus 2 lambda. Solve, lambda equals minus 3, and t equals minus 2. Check the k component, 3 times minus 2 equals minus 6, and 6 plus 4 times minus 3 also equals minus 6. So t equals minus 2. OA equals 8i minus 5j plus 6k. Line L passes through A, parallel to 2i plus j plus 4k. Part C. Line M is R equals 5i minus j plus 2k, plus mu times ai minus j plus 3k. The acute angle between L and M has cosine theta equals 1 over root 6. Find A. Now let's work through the solution step by step. Line L has direction 2, 1, 4. Line M has direction A, minus 1, 3. The angle between two lines uses only their direction vectors. Cosine theta equals dl.dm over mod dl times mod dm. The dot product is 2a minus 1 plus 12, which is 2a plus 11. Mod dl is root 21. Mod dm is root a squared plus 10. Set equal to 1 over root 6, square both sides, and expand to a squared plus 88 a plus 172 equals 0. So a equals minus 2, or a equals minus 86. So a equals minus 2, or a equals minus 86. Question 10. A differential equation for a draining tank. A cylindrical tank has base radius 4 meters. The water depth is h at time t. Water flows out at a rate proportional to the square root of the volume. Part A show that dH by dt equals minus lambda root h, where lambda is a positive constant. Now let's work through the solution step by step. Derive the differential equation for the water depth. Step 1. Volume is pi r squared h. With r equals 4, v equals 16 pi h. Step 2. Differentiate, dv by dt equals 16 pi times dh by dt. Step 3. Outflow is minus k root v. The minus means water is leaving. Step 4. Replace v by 16 pi h. That gives minus 4k root pi times root h. Step 5. Set the 2 dv by dt equal, then divide by 16 pi. Step 6. So dH by dt equals minus lambda root h done. So dH by dt equals minus lambda root h, as required. A cylindrical tank has base radius 4 meters. The water depth is h at time t. Water flows out at a rate proportional to the square root of the volume. Part B. At t equals 0, h equals 4. At t equals 20, h equals 2.25. Solve for t in terms of h, and find the time to empty the tank. Now let's work through the solution step by step. Step 1. Separate, h to the power minus a half dh equals minus lambda dt. Step 2. Integrate both sides, 2 root h equals minus lambda t plus c. Step 3. When t is 0 and h is 4, c equals 4. Step 4. When t is 20 and h is 2.25, lambda is 1/20. Step 5. So 2 root h equals 4 minus t over 20. Step 6. Rearrange, t equals 80 minus 40 root h. Step 7. Empty tank, h equals 0 gives t equals 80 minutes. So t equals 80 minus 40 root h, and the tank is empty after 80 minutes.